Categorified hyperbolic geometry.
Thank you very much. And it's really an honor and a pleasure to be invited here to celebrate the birthday of Francis. Part of the work Francis has done over the past few years has involved quantization of hyperbolic geometry. For example, in 2 dimensions, one can construct, as has been discussed more carefully in many other talks here, one can construct a moduli space of flat connections on a surface. It's convenient to complexify, use SL2C. Then this is an algebraic object, and one can consider the ring of functions of the space. The classical trace functions give you generators for this. So taking the trace of the holonomy around various loops in sigma, and then quantization in one interpretation amounts to promoting amounts to deformation quantization of this ring. So this happens to have a holomorphic Poisson structure. One can do deformation quantization with respect to that, and at least abstractly get some quantum algebra, which is the thing that Fock and Chekhov studied, and the thing you're supposed to get from skein modules. From skein theory. In the case of a punctured surface with an ideal triangulation, there is a nice description of this algebra, kind of a nice local description, using quantized shear coordinates, or Fock-Chekhov coordinates, or Fock-Goncharov coordinates associated to the edges of the triangulation. They satisfy a very simple Q commutation relation for 2 edges that share a triangle. xy is qys. So I'd like to discuss some ideas about categorifying this story. This is part of some ongoing work with Davide Gaiotto and Greg Moore. Some things I can be concrete about, others I really can't yet, but we're working hard on it. So part of this talk should be treated as inspiration, kind of what physics says or about what should be true. And I kind of want to explain where things are going. Okay. In the case of a surface, I'll explain later that categorification means promoting functions, at least the categorification I have in mind, means promoting functions to a category, C of sigma, such that the growth indeed group of this category is the same as the classical ring of functions. But first, I'll actually start in 3 dimensions. So come back to that in the second half of the talk. So in 3 dimensions, goal 1 of categorified hyperbolic geometry is to take a 3-manifold M say, a hyperbolic three-manifold, and produce a graded vector space with a differential. In other words, some linear operator on the space that squares to 0. That has some properties. So to explain the properties, let me explain the gradings. There are two canonical ones and several extra optional ones that come about when M has a boundary. So the canonical gradings are, I will call R and J. So R is the homological grading. And it's called R because in the physical theories that this comes from, R is coming from a so-called R symmetry. It's a symmetry that many supersymmetric theories have. And then there's a non-homological grading, which I'll call J, that is called J because it comes from spin. And J is the letter that denotes spin. And there may be others. So one thing one can do with this vector space is take its Euler character. So
how Q respects J?
Right. So Q commutes with J.
Huh? Commutes.
Q commutes with J. So usually, Q is going to be some supercharge in a supersymmetric theory that usually doesn't commute with spin, but there is a combination of spin and R symmetry that does commute with Q, and that's what I'm denoting J for this talk.
And Q changes R by 1?
And Q changes R by 1. So the Euler character, it's like a trace over the space of -1 to the R. I can take a graded Euler character to communicate Q to the J, and again, there may be other gradings that come in here. But I want this Euler character to have one very important property. Namely, as Q goes to 1, I want this to diverge and have a leading asymptotic governed by the hyperbolic volume of M. Now, okay, if that's all I wanted, I could actually try to achieve this with the categorification of the Color-Jones polynomial, invoking analytic continuation in the volume conjecture to try to get limits like this. I'd actually like to do something a little different and a little more intrinsic related to SL2C Chern-Simons theory rather than SU2 Chern-Simons theory, which gives Color-Jones polynomials. And I actually want this Euler character to be the SL2C partition function, SL2C Chern-Simons partition function on M at level 0. Now, I should explain what that means, since probably most of the audience is not familiar with the parameters for SL2C theory. So SU2 Chern-Simons theory depends on a level k, and in Jones polynomials, Q is a kth root of unity. SL2C Chern-Simons theory depends on two levels. K, which is an integer, and called sigma, which is real and continuous. Setting k to 0 doesn't trivialize the theory. You've still got sigma around. And in fact, at k equals 0, partition functions depend, well, end up being a function of q to the half, which is e to the pi over sigma. And so one gets, for example, Laurent series, in fact, infinite Laurent series in q to the half. And so these are exactly the kinds of partition functions that look like Euler characters. Our spaces are going to be infinite dimensional, but will have finite graded dimension. Okay, so for example, let's take an ideal hyperbolic tetrahedron. The hyperbolic structure is parametrized by a complex number z, shape parameter, and the volume made well, suitably complexified. It's basically the dilogarithm of z, as Hashai had mentioned this morning. So the space h of delta is going to be triply graded with the usual R and J gradings, and an extra grading E, which I'll refer to as a flavor grading, a flavor symmetry. Let me introduce a little bit of notation. So in order to speak fluently about, or easily about, these graded spaces, I'm going to denote, well, I'm going to denote lines by their characters. So I'll use T to denote a copy of C in R grading 1, in R grading 1, homological grading 1, with the other grading 0. And I'll use Q to the half to denote a copy of C with J grading a half. And I'll use Z, it's going to be the same Z, to denote flavor grading 1. And then 1 is just going to be the copy of C in grading 0. Okay. And then monomials, something like T cubed squared Z cubed, are just going to represent tensor products of the respective lines. So that's an obvious thing. It's C in gradings 1, 2, 3. And then I can take direct. So there's an implicit tensor product in multiplication, and I can take direct sums and so on. So the main ingredients that go into constructing H are Fock spaces. The other part. So if I consider an expression 1 plus x, where x is some monomial, some line. This is a two-dimensional space. I can think of it as the vector space of the exterior algebra in some variable x that has the same charges, the same gradings as the x line appearing here. And this is a simple fermionic Fock space. It's the thing you get by acting on a vacuum, 1 with a fermionic operator whose square is 0. So I can act once and then I'm done. And there's a bosonic version of this. 1 plus x squared plus dot dot dot, which is the vector space of the symmetric algebra. Which in shorthand can write as 1 over 1 minus x. So minus signs are allowed when they're in the denominator. Then the Hilbert space for the tetrahedron can be expressed in 2 ways, both of which are important. And they're not quite equivalent, but both of them come up. So there's a fermionic version. It's the tensor product of an infinite number of fermionic Fock spaces. And there's a bosonic version. Which is a tensor product of an infinite number of bosonic spaces, but now there's going to be a t involved. Okay. Right, so both of these spaces have finite dimensional graded components. So I can write them as a direct sum of graded pieces where each piece is finite dimensional. So even though there are lots of infinities happening, they're very controllable infinities. What I haven't said is how the differential acts, and I'm just going to define it. The right thing to do in this case is to define it to act as 0. In both cases, it's obvious that it has to act as 0 on the fermionic space because there's no homological grading. There are no t's here. It could potentially be non-zero in the bosonic version, but it turns out not to be. And if I take Euler characters, I end up getting standard quantum dilogarithm functions. So taking an Euler character just amounts to setting t to -1 and thinking of direct sums as ordinary sums and tensor products as ordinary products. And so both of these become versions of the quantum dilogarithm function. So as t goes to -1, get a quantum dilogarithm, and if additionally I send q to 1, these 2 respective characters behave like e to the plus minus 1 over log q times a dilogarithm function, depending on z, hence the volume of an ideal tetrahedron. Okay. The general story, I can give some physical motivation for, though I can't yet do systematic calculations. So what's the idea? there's something that's been called the 3D correspondence. So in physics, it comes about from the existence of an essentially canonical quantum field theory in 6 dimensions. So there exists a 6D SCFT, which means supersymmetric and conformal quantum field theory with maximal supersymmetry that I'll just call theory X, following some mathematicians who have studied the subject. It's labeled by a symmetry algebra of type A, D, or E. And we just want the A1 version here. And otherwise, it's thought to be unique. So you give me a symmetry algebra, there's a unique maximally supersymmetric theory in 6 dimensions with that symmetry. This is not a topological theory. Its value on a 6 manifold depends on the conformal structure of that manifold. If we put theory X on a 6 manifold, that's the product of a 3 manifold times R3. And scale down M by a conformal transformation, we expect to get an effective theory T of M on R3. And so it's a theory that is canonically associated to the 3 manifold M. Now, in principle, it could depend on the conformal structure of M, but if M is hyperbolic, the conformal structure is essentially unique, or there is a preferred one, in which case one gets topological invariance of the 3 manifold. So this thing is a topological invariant. So one gets something like a TQFT that's valued, that assigns to M not a number, but an entire quantum field theory. And this is a supersymmetric, so again, this T of N is not topological. The T of N is supersymmetric and conformal. So it's supersymmetric and conformal. The cool thing about this is that anything you calculate in this theory T of N ends up being a topological invariant of M. And there is a conjecture early on in my work with Gukov and Hollins, and with Gayoto and Gukov, and the work of Yamazaki and Terashima, that partitioned functions of T of N on simple spaces like length spaces so partition functions of T of M on OK1, which is ZK quotient of the 3 sphere. And again, I can also interpret this as partition functions of theory X on M times LK1 in 6 dimensions. should be equivalent to partition functions of SL to C Chern-Simons theory at level K on M itself. And then this assertion was proved in quantum field theory by Cordova and Jafferis and Lee and Yamazaki and Junya Yagi, and for all sorts of different values of K. So this is something that physically we are completely certain about at this point. So this is a QFT theorem using path-integral arguments. Okay. Presently, we're interested in Chern-Simons theory at level 0, which means computing such a partition function on S2 times R. In general, times S1. In general, I'm going to let the background be D times S1, where D could be S2 or possibly R2. And occasionally different choices are more relevant. The tilde and the product means that the geometry is not a direct product, but a sort of fibration where as I move along the S1, D spins. Whenever a geometry involves a circle like this, the partition function, the one I'm talking about, the partition function takes the form of a trace over a Hilbert space. So in this case, it's a trace over the Hilbert space of T of n on D, R2 or S2 of, well, if this were a topological theory, you might think I just stick 1 in here. Because there are fermions involved, and this is a supersymmetric theory, there's a -1 to the R. And because the geometry is spinning, there's a Q to the J. Possibly other stuff. And that's the partition function I wanted at the beginning of the talk. I've erased it now. And this Hilbert space of T of n on D is the H of m that I introduced at the beginning. So in the simple example of an ideal tetrahedron, oh well, it's gone now. Right, so in our example, T of n turns out to be the simplest possible theory one can have, the simplest possible supersymmetric theory one can have in 3 dimensions. It's the theory of a free bosonic field and a free fermionic field. This one phi, and there are some symmetries in the theory. First, there are space-time rotations. That's the spin, J. Then there is so-called U1 R symmetry that rotates, I should say these are complex, that rotates the phase of phi with weight 1 and doesn't do anything to psi. And there's a so-called flavor symmetry that rotates both of them with the same phase. The supercharge here acts on phi to give psi. And so to connect with Sasha's question from the beginning of the talk, U1R does not commute with supersymmetry, and the flavor symmetry does, because it acts on these fields the same way. H of the tetrahedron is a Fock space built from modes of either the boson or the fermion, or if we're on S2, possibly both. On D. So if we're on R2, it's one or the other. If D is S2, you actually use both. The spaces I wrote down at the beginning of the talk were one or the other. Okay. Right, so here the computation can be just done directly to produce the Hilbert spaces, or these vector spaces I talked about, and the reason that the supersymmetry acts trivially is because essentially this is a free theory. Okay. So more generally, the expectation is the following. So if the first part of this is not expectation, if M is a hyperbolic manifold with an ideal triangulation, we can explicitly construct the theory T of M. And by construct, I mean write down a bunch of fields in a Lagrangian that determines its interactions. It has the form of a product, tensor product, of a bunch of tetrahedron theories with symmetric interactions coming from the gluing. That suggests that the Hilbert space, the vector space, whatever, it's a Hilbert space in T of M. The Hilbert space that we assign to this triangulated 3 manifold should be a product of these very simple Fock spaces assigned to tetrahedra with a non-trivial differential that takes into account the fact that we're gluing things together. And so this is obviously easy to describe. The differential is rather difficult to describe. Okay. So that's what I want to say about purely 3D. Before moving on, I should relate this to other things that have been done before. So the 6D setup, where I'm looking at theory X on M times some twisted product, S1, or if I want the Hilbert space, I should replace S1 with R2, sorry, with R time, is exactly the geometry that Witten used a few years ago to describe categorification of the Jones polynomial in a physical context. In that case, M was just R3 with a knot inside. given by a certain defect in the 6D theory. Going back many more years, if we lift to M theory or string theory, so this field theory can be lifted to some M theory or string theory construction that is precisely the geometry that Gukov, Schwarz, and Waffe and Dunfield, Gukov, Rasmussen used to produce triply graded homologies related to Jones or Humphrey polynomials. Doubly or triply graded, depending on exactly how it's done. But this is categorification from counting BPS states. In M theory. Okay, so just wanted to say that to emphasize that everything is kind of connected. So what I'm describing is a particular viewpoint on constructions that have been around for a while. This sort of the Fock space that I described for the tetrahedron was one of the central ingredients in the description of Oguri and Waffe of open topological string partition functions for the same reason. Yeah, everything is connected. Okay, so back to surfaces. So goal number 2.
Peter, but before you go to goal number 2, for example, the pentagon relation, like product of 2 Hilbert spaces equals quasi-isomorphic to product of 3.
Yes, so I will say this at the end of the talk. That is what we're building up to. Okay, so goal 2 is categorifying hyperbolic geometry is to take a surface and assign to it a tensor category, monoidal category. Such that the growth and beat group of the category is the same as the ring of functions on the moduli space of flat SL2C connections on sigma. Now, right, so growth and beat group is usually a group. It's an abelian group. In the case that our category has a multiplication, it becomes a ring, and that gives the ring structure. So there are a few other things to say here, some little adjectives. So if we want to quantize the algebra and make it non-commutative, then there's a twisted tensor product that's involved that I'll give an example of in a little bit. And this thing is a DG category, differential and graded, because there's supersymmetry around, and there's always a differential. To a 3-manifold, 2 surface. We want to assign something else. So if, for example, if M is a cobordism, so its boundary consists of the union of 2 surfaces, sigma 1 and sigma 2, then we should get a functor from the category associated to sigma 1 to the category for sigma 2. And in the special case that sigma 1 and sigma 2 are empty, so if M is closed, then this is a functor from the category of nothing to the category of nothing, where the category of nothing is graded vector spaces. And this functor just acts as tensoring with the space H of M that I introduced before. Okay, now again, the reason such a structure exists comes from 6 dimensions. So if we put theory X on a Riemann surface times R4, we get a 4-dimensional supersymmetric conformal field theory T of sigma. This was defined and studied by Gaiotto and Gaiotto-Moore-Knightsky. It is in physics called a theory of class S. It's been studied by many, many other people since. And one of the main results of GMN this is where the category C of sigma comes from. So C sigma is supposed to be the category of line operators. In T of sigma. And one of the main results of GMN was that the Grothendieck group of this category is what it's supposed to be, is the ring of functions on the moduli space of flat connections. And so they said this without actually describing the category, because there's a more direct description of this Grothendieck group. Okay, so I should say, why do line operators form a category in the first place? So line operators in any theory with a suitable topological twist form a category. If I have two line operators, L1 and L2, I can place them end to end. So these line operators are objects supported literally on a line in the theory. These are, so an example are Wilson lines in transassignments theory that Witten used to include knots. So if I put two of them back to back, there is a space, a vector space of local operators that can be inserted between them, and that's the home space. And the tensor product comes from collision. I throw two line operators at each other. They become a new line operator, it's L1 tensor L2. So here, we want this theory T of sigma, want to look at it on D, which is S2 or R2 times time times another spatial dimension. Or equivalently, we're looking at theory X on sigma times D times time times space. With line operators at the origin of D, or one of the poles of S2, times time times points in space. And so the picture ends up looking like this. We have D, we have time times D times space, where D is, well, D is spinning, but not in space, it's spinning in time. And the line operators are all forced to live at the origin of D. And they're extended a long time. So L1, L2, and so on. Everything is graded by rotations of D. That's where the Q grading J comes from. And if we keep track of this grading, the order in the tensor product matters. So these line operators are occurring in a particular order. And doing the tensor product in the opposite order changes the Q grading of the result. So the order in the tensor product matters. So it affects the Q grading. So as an example, if we have a surface with an ideal triangulation, then each of these coordinates, x and y, and z and so on, get promoted to objects in this category. And the tensor product of x and y is the same as q times the tensor product of y and x. Where putting a q out front means that I'm tensoring with a line with a copy of C that has J grading 1.
Is this a triangular category?
This should be an infinity category in its full glory. Simply because I can reduce this picture along D to something two-dimensional, and it's a category of lines in a two-dimensional A model.
But you didn't explain why x and y promotes to this line operators. You stated.
I didn't explain this. I'm not sure I have time to, but it is something that is not a mystery. So this comes from work of GMN, who described these coordinates as expectation values of line operators in an abelianized theory. The trace functions are expectation values of line operators in the non-abelian version of T of sigma. This is something you know. How do three manifolds fit in?
So the lines are just lines in the surface, in sigma.
No, they're lines along time. They also happen to be lines on the surface, but that's here. So they wrap. There is some curved gamma that labels them times, and they wrap time as well. So they're in 6 dimensions. They're 2-dimensional objects, and so they are labeled by. They happen to be labeled by a curve in sigma as well, and that's where you get trace functions. The x and y are curves in the spectral cover. They're labeled by curves in the double cover, in this case.
So is it possible to hint at how to lift, how to lift function to the category, or is that not the crucial issue?
That is absolutely the crucial issue, and we have some hints, but not a systematic description. So there are hints from this very short paper that Gayota, Moore, and Witten put out a few weeks ago, coming in at just under 500 pages, on Landau-Ginzburg models and infinity categories. So they study something that, well, should sort of be a construction of this category. But I want to make the statement that this category exists in case it happens to inspire anyone to look for it. And some of the properties that it has. So 3 manifolds fit in the following way. So if the boundary of a 3 manifold, well, if you have a cobordism, then T of n is an interface. It's a 3-dimensional theory that lives in 4-dimensional space. So in the picture I had up there, T of n is a particular slice in the space. It separates T of sigma 1 from T of sigma 2. The functor on that takes us from category C of sigma 1 to C of sigma 2 is in pictures pushing line operators through the interface. So this is passing through. In the simplest example, I can describe a little bit better what's happening. So if M is a tetrahedron, we can think of the boundary of the tetrahedron as two triangulated squares, and then cobordism through M is a flip. Taking a triangulation of the surface that locally looks like that to a triangulation of the same surface that locally looks like that. At the quantum level, in the quantum algebra, the flip produces a cluster mutation. So any quantum function gets conjugated by a quantum bilogarithm. So if I have a flip on x, it sends any L to to L conjugated by that, where QdL of x is the product and goes from 0 to infinity, 1 plus q to the n plus a half x. So what do we expect? I should also say, you can sort of visualize why this is a conjugation. What happens if I take a line operator on one side and push it through the interface? I get a line operator surrounded by a little bubble of interface, which is where the conjugation is coming from. At the categorical level, we expect the same sort of conjugation operation, but now we're tensoring with Fock spaces. So in the category, L should go to phi bosonic L, and psi fermionic of x, and here of tx, where psi of x is the thing I had at the beginning. So psi fermionic, sorry, I should probably call them x in both cases. Psi fermionic is the product 1 plus q to the n plus a half x, where now x is some object in this tensor category. It's multiplied by a line, then I'm taking direct sums in a big tensor product. And psi bosonic is roughly the inverse. Okay. So this is easy to describe. Figuring out what the new differential is hard to describe, and that's again one of the main issues that we're trying to deal with. So it's not just tensor product, but the differential gets deformed. There is a fun consistency check that all this makes sense though, and that's the 2-3 move. So if any of this has even a chance of being true, we need to make sure that flipping through two edges of the pentagon and flipping through 3 edges of the pentagon does the same thing. We can analyze that by looking at characters. So it means, so I'll be done in a minute. So it means that for x and y, such that xy is q yx, and here I mean that twisted tensor product, we need psi fermionic of x times psi fermionic of y to be equal to psi fermionic in y psi q to the half xy psi of x, and a similar thing for the bosonic ones, except reversed, because they're coming in here from opposite sides. So So psi y times psi of x equals psi of x psi of q to the half yx psi of y. The first one is true on the nose. There are no homological issues to deal with.